Start. Okay, hi everyone, good morning. So today we will talk about model fitting, ransack, and how to solve the 5-point algorithm. So let's go. Once it lets me move. Okay, sorry. So let's warm up with the problems that you're probably familiar with. The problem of line fitting. So many problems require fitting a model to noisy measurement. The simplest of all is line fitting. In line fitting, you're given a set of points. And the problem is to pass a line through the points or near the points, what's called linear regression. The important thing to remember is that the results depend on the noise model. So so we will see three noise models really. The first one is the familiar linear least squares. So in linear least squares, so let's see, the model is a line. So ax plus b should be y or f of x, okay? The measurements yi are given with some noise. So it's the true yi plus epsilon I. The unknowns are a and b, the parameters of the line. Okay, so xi and y are unknown. Xi and yi hat are known. And epsilon I, we assume is distributed as Gaussian with zero mean and sigma square. And so the probability for noise is the usual Gaussian equation. The probability of noise in all n points, we assume that they're independent. And so it's the product of these Gaussian functions. So what we will want to do is to minimize the log likelihood. And so we write the minus log of the joint probability. And if you take the log, what you get is n times this half log of 2 pi sigma square plus what was in the exponent, which is the sum of epsilon I square divided by 2 sigma square. Now, we want to minimize or find A and B that minimize this minus log likelihood. We can notice that the first term is independent of A and B. The second term contains epsilon I, and so it depends on A and B. How? Simply epsilon is the difference between the y and x value that we saw, right? That we measured. Okay, and so really we just need to minimize the second term. The sigma square is constant and we can exclude it from the minimization, and so we get just minimized over A and B of sum of epsilon I square, which is the minimum of the difference yi minus axi plus b squared. Okay. And so we can write this as linear least squares problem. So here I'm writing this as a matrix equation. So for every point, we have a row x1, 1 times AB. So, okay, so it's AX1 plus B minus y1, etc. And we want to take this vector, the result is a vector, square norm, and minimize it. Okay, so this is written here. And the minimum, as you know, is obtained through the pseudo inverse. So usually we assume that we have at least as many points as the number of parameters. In this case, at least 2 points. And so this is the pseudo inverse, which gives you the solution. Okay. And the solution looks like this. Essentially, we allowed the y value to change, and we try to minimize that change. Okay, so you can see that at each point, the difference here in this minimization is exactly this, the length of these red lines, which are all parallel to the y-axis. Is it clear why they are parallel to the y-axis? You're welcome to say yes when I ask, or no if. Okay. Okay, so this is the linear least squares solution, and it is useful when the x value is known accurately, but the y value is obtained with noise. Now, if, for example, we're getting an image and somehow we want to pass points, pass a line through some points in an image, there is no one axis that is preferable in some sense. And so this leads us to a different noise model and the solution to a problem that is called total linear least squares. Okay, so that's the second type of solution. Okay, so let's look at that. So now we are going to assume that the noise is in both coordinates, in x and y. Okay, so x hat and y hat are given by the true xy, which are unknown, plus delta I, and delta I is a vector in R2, and you can think of it as some delta x and delta y. Okay. Again, we assume that the probability of the noise is Gaussian, IID. And so the usual Gaussian equation, now we take the norm of delta I in the exponent, and we assume that the noise in x and in y are of equal variance. And so we just divide by 2 sigma squared. Okay. Again, we take the minus log likelihood. We get the first term, which does not depend on delta. Okay. And we will be able to omit it from the minimization. And the second term is just the exponent, 1 over 2 sigma square. Again, we can take that out of the minimization, times delta, the norm of delta square, which is just xi hat minus xi square plus y hat y I hat minus yi square. Okay, and the true xi and yi are given by the model. Okay. So, so let's look at this again. This equation, the norm of delta I, is just the distance squared between the measured point x hat I, y hat I, and the true point xi, yi. And that's and the true point is any point on the line. So we essentially minimize the distance of our measurement to the line. And so what is the distance of a point from a line? We can write it as, we just plug in the point into the line. It should be hats here, actually, if we're, right? If we want the distance from xi, yi from a line, or xi hat, y hat from the line, we plug in into the line equation, axi plus byi plus c, and take absolute value. But we also need to normalize the coefficients of the line a and b, so we need to divide by a squared plus b squared square root. If we don't do that, we obtain a scale distance. Okay, and since we don't know what are a and b, we have to normalize. Otherwise, we may get the wrong line in the minimization. Okay, so so to minimize the equation, to solve the problem, what we want to do is to minimize the distance of our measured xi, yi to the line, okay, squared, subject to the constraint that a squared plus b squared is 1. Okay, clear? So how do we solve this? Let's look first at the derivative of this distance squared. If we take a derivative with respect to c, what we get is, right, 2 sum axi plus byi plus c equals 0. Okay. The constraint does not depend on c, so we can do that. And that implies that c will be simply minus the a times the average, or the average of x plus b times the average of y, where the average x and y are simply the centroid of the endpoints. Okay. So this implies that the best line, the line that minimizes this difference, will have to go through the centroid of the points. And that's typical in total least squares problem. Okay. So what we shall do next is just eliminate c. So we'll move our coordinate system such that the centroid will be the origin of the coordinate system. Okay, so essentially you take xi and subtract from it the average of the x's, yi minus the average of the y's. Okay, so this is what we do here. Okay, we replaced xi. The new xi is xi minus x bar. The new yi is yi minus y bar. And now we change the problem to minimizing axi plus byi squared, c is 0 in this case, because the line should go through the origin, subject to the constraint that a squared plus b squared is 1. Okay. This equation, this minimization, we can write in matrix equation, in matrix notation, sorry. You can see that here, this is a quadratic equation. So if you write sum xi square, sum xi yi, and in the second line, sum xi yi and sum yi square, and multiply from the two sides by the vector ab, this is what you get. So this quadratic equation can be written as a quadratic form, okay, where m is known, M contains our measurements, which is a second order moment over the points. Okay, and T contains the unknowns, which are A and B, the coefficients of the line. Okay. And the constraint is that the norm of T is 1, or the norm square of T. T transpose T is 1. Okay, so we simply rewrote our problem in matrix notation. And we got the second order moment. Okay, it's really, and the second order normalized moment, normalized because we took out the, we made the first order moment to be 0. The first order moment is the average of the point. Okay, so now we want to solve this quadratic equation, and you must be familiar with this. The solution should be an eigenvalue problem. Let's see how. So first we write this as a Lagrange multipliers problem. Okay, so minimize T and lambda, the Lagrange multiplier, of the objective T transpose MT plus lambda times the constraint. The constraint is 1 minus T transpose T, okay, because we wanted T transpose T to be equal 1. Okay. So let's take a derivative with respect to T. Okay, the gradient with respect to T is a two-dimensional vector, so it's a gradient. We take a gradient of T transpose MT. Okay, the gradient will be MT. Okay, this quadratic equation becomes linear. Okay, and lambda times the gradient of 1 minus T transpose T. So that will become lambda T. Okay, and minus lambda T. And so the gradient with respect to T of the Lagrange optimization expression gives you MT equals lambda T, which shows that T must be an eigenvector of M. Okay. Now the eigenvectors, so there are a few eigenvectors. In this case, there should be 2 eigenvectors, right? Because this is a 2x2 problem. Okay, in general, the eigenvectors are critical points. And the one that minimizes this equation will have the smallest eigenvalue. Okay. Notice also that if we took the derivative of lambda with respect, if we took the derivative of this Lagrange expression with respect to lambda, what we get back is the constraint that T has norm 1, which is good. So essentially, T is an eigenvalue, T is an eigenvector with norm 1. Okay, so again, the minimum is given by the eigenvector of smallest eigenvalue. And if we plot this, now the solution looks like this. We find a line such that all these distances between the measured points and the line, the minimizing the solution, these red lines are orthogonal to the line that we found. Okay, so this is the solution, the line that goes with smallest distance to our measurement. Okay, questions? Okay. So in geometry, in computer vision, the main kind of problems, and some of them you already seen in previous classes, are problems where we need to find either the camera or the 3D points. So let's go back to these problems, and the problems are of the same sort, the same nature. We have some equations, and we want to minimize over errors, and everything depends on the error model. The solution depends on the error model. Okay. So here we look at the problem of either camera or 3D point recovery. Okay, we want to compute camera's PI given matches between 3D points in images, between 3D points xi and image points, small xij, xj and xij. Okay, so you're given, suppose we know the scene, we're given xj, capital Xj, and we have image points xij, and we want to solve for the camera PI. Okay. Okay. And a second problem that will be essentially the same is the following. Suppose we are given 3D points. Sorry. Suppose I made a mistake. Sorry, let me repeat that. Let's start again. Excuse me. Okay, suppose we are given 3D point xj and image point xij. Okay, so we know the scene and we know and we have the projections, and we want to compute the camera's PI. Okay, that's the first problem we will look at. And the second problem, which is essentially almost identical, is when we know the camera's PI and we have the projections of the point xij, and we want to compute the scene, capital Xj. Okay. So we know that the projections, small xij, is given by these equations, which are simply the perspective projection after applying the camera matrix. Okay, so let's see. PI, the camera PI, is applied to xj, and we divide it by the z value. So 1, 2, 3, the superscript here are the rows of PI. Okay, and we have some noise, delta ij. Okay, and you can see that the role of PI and xj is the same in this equation. So this is why we get these two problems that should have essentially the same kind of solution. Okay, so either we want to find PI or xj when the other one is known, and in any case, the measurements include the small xij, which are also known. Okay. Okay. Again, delta ij. Delta ij will generally can be assumed to be Gaussian, or in many cases can be assumed to be Gaussian, and then we will have a solution that is very similar to the one before, except that this is a more complicated equation. Okay, so let's see what we can do. One possibility is when we assume that there is no noise. Okay, if there was no noise, if delta was 0, okay, what we could do is multiply this equation by the denominator. Sorry, there is noise here. We could multiply out the denominator, okay? And then we get equations like this, which are linear in both the cameras and the scene points. Okay, so if we want to solve, so quadratic really, if we want to solve in this case for pi or for xj, given that the other one is known, then we simply solve a least square problem, and this is simple. The problem here that the reason we don't like this solution is that here we didn't assume anything about the noise. In general, the noise should be in the measurement. And if we assume that delta is Gaussian, then we can't solve, this would not be the appropriate problem to solve. In that case, we will need to solve an equation like this, which is nonlinear, okay, or non-quadratic, non-polynomial, okay, where we cannot multiply out the denominator, okay? So this cost function, the first one, we call an algebraic error cost function, whereas this one we refer to as geometric error. Okay, we understand why we call this geometric and this algebraic?
No, can you explain?
Yes, yes. So the basic idea is that, so let's take the second one first, okay? The second one tells you that you have the measurement xij1 and xij2, okay? Is that the x and y values, the position of a point, okay? And the minimization will tell you where capital Xj, the scene point, should be projected to in the ith image, okay? And you look at the distance in the image between the projection and the measured point, okay? And now, assuming that your algorithm for point detection is making mistakes that are basically Gaussian, you expect that this distance will behave like a Gaussian. So the bigger the distance, the smaller the probability will be, okay? So this makes an intuitive sense, right? Now, if you go to the first equation, you notice that it's not the case. What happens here is that you take the measurement, the x and y, or what's called here xij1 and xij2, okay? And you multiply them by the z value. And then you take the distance to the x value of the scene. So it's like you're taking a distance in a completely new space, which is really in the 3D space, which is unknown. So the error here does not correspond to any sort of sensible probabilistic model of your measurements. And that's why we call it an algebraic error. Okay, so it's motivated by algebra, not by the geometry of the problem. Okay, so in general, we would want to solve equations like this, like the geometric error, not algebraic error, as much as we can. However, as you can see, usually equations that when we use an algebraic error, it leads to a simpler problem to solve. And so often that would be like an initialization to solving an algebraic error, to solving the geometric error, okay? Okay, so far we assume that there are no outliers. We assume that every measurement is very close to wherever it should have been. And the appropriate model of error was Gaussian. In reality, in many cases, we also have many outliers. This is particularly the case when we are trying to match between images or match between images and scenes. Okay, so I think we talked in one of the previous classes about SIFT, basically a method to match between points in images. And we said that it was based on some local measurements around the point. And naturally, you expect many outliers. In this case, you have the scene that contains this teddy bear. The teddy bear appears here in the image. Here, this is a very good case where most of the true matches, most of the matches are true. Those are the green lines here. But occasionally, there are some bad matches. And we have to, if we try to solve a least squares problem, it will fail very badly because of these outliers. Okay. In reality, it could be even that only 10% and fewer of the matches are true. So it depends on the scene, how complicated it is, and how much clutter there is in the image. Okay, so visually, if we have data here and we want to, if the model is a line, okay, if we try to do a least square fit, so let's do, so the data really lies on the line, but there is just one point that is outlier here, but it's very distant from the actual line. If we try to do a least square fit, this is what we will get. So this point will have relatively very high weight because the distance will, we will try to minimize this big distance. And so the line we really will minimize the least squares, but would not be what we want. Okay. If we apply a robust fit, so a robust fit is any method that can identify the outlier and either remove them completely or just weight them, give them very small weight. This is what we're supposed to obtain. You can see that assuming that indeed there are outliers, it's good to remove this outlier and then obtain a good solution. Okay. So how do we solve, how do we have a robust method? So there are different methods. This is not the only one, but the one that is often used in 3D reconstruction is Ransack. You learned a little bit about it in the introduction course, and we're going to repeat it now. The advantage of Ransack is that it allows for relatively many outliers. Okay, so other methods, most other methods are based on a reweighting of the points, and those usually, many of them, not all of them, many of them require initialization. And because of this initialization, they can deal with only 10% or 20% outliers. Ransack can deal with more than 50% outliers, and even many more than 50%. Okay, so it's that's why it's so useful in reconstruction problems. Okay, so how does it work? So the idea is given a set of points, a set of, so for example, this could be a set of matches, okay, or any other pairs of things, xi, yi, okay? And assume we have a model which we will denote as fxy equals 0, okay? So this could be a line in the previous example, or this could be a projection given camera and 3D point projection to 2D point, or an essential matrix, etc. Any model. Okay. The idea is very simple. First, we select a small subset of measurements. Okay. how small or how big, the number of measurements should be sufficient to evaluate the model. Okay, so how many points do we need to, in the case of estimating a line? In the previous problem? Let's go to the previous problem. Sorry.
We need 2 points.
Right. Every 2 points determine a line. Okay. So, so we select a subset that determines the model. Then we take all the rest of the points and see how many of them form what we call a consensus set. Okay, so we decide on a threshold, and we, for all the points in T minus S, okay, we test the error of the model. Okay, and if the error is less than a threshold, then we put this pair into the consensus set. If the error is bigger, then it's not in the consensus set. And finally, we simply, and we choose the model that yields the largest consensus set. Okay, and we repeat this many times. At each time, we choose another subset, form a consensus set, and finally take the largest, the solution that gives the largest consensus set. Okay. Once we decided what is the consensus set, the best consensus set, then we assume that all the points in the consensus sets are inliers, and so then we solve a least square problem. Okay, that's the idea. This is simple. Yes.
What are the different models here? I mean, you in section 2 you select the model that deals the largest consensus set, but what is the difference between the models?
Yeah, that's a good question. So let's go back to this problem, this simple problem. We want to find a line. Okay, so we select a pair of points. So let's assume that the first pair that we took is a point here and this outlier. Okay, we estimate the line through these points. That will be a line that goes like this, right? So it will be diagonal in this direction. Okay, thanks for plotting it. Okay, now maybe these 2 points will be in the consensus set. So overall, we have 4 points in the consensus set. Okay, next we take 2 points here, and we get a line in this direction. And let's say it gets 20 points in the consensus set. Then we will prefer that line over the first line, okay? And so forth. And so you assume that a line that more or less in this direction will give you the largest consensus set. And over that set of points that are close to this line, we will do the least square.
So basically, in each iteration, you choose the set on which you build the model?
Exactly.
Okay.
A minimal set, in this case, only 2 points, okay, which determine the model. And now we have a set of models. Each of them gives you a consensus set, and you take the models that give you the largest consensus set. Okay?
Ronen?
Yes.
I know that there is also something that checking the ratio between the inliers and outliers during this procedure.
Here, the total number of inliers and outliers is constant, so there is no reason to look at the ratios. I'm not sure what you refer to. You can ask me in the break. Okay.
I think that maybe refers to the number of experiments that you need to do with respect to the ratio of the inliers and outliers.
Okay, this is exactly the next step.
Okay.
The next thing I'm going to talk about. Okay, how many iterations do we want to make? Okay. So suppose the model requires k measurements. So in the previous example, it was 2. Okay, with, for example, with an essential matrix, we need k equals 5. Okay. And let's assume that Q is the fraction of inliers. Now, in general, we don't know what fraction we will have. But we can say, well, we can solve this problem when the fraction is, I don't know, 80%, etc. So we can aim at a certain fraction, given some statistics that we do. Okay. So the question is, how many ransack iterations are needed to draw k inliers with probability p? So I give you a probability of success, and I want to have many drawings to reach that success value. Okay. So let's see. So the chance of drawing k inliers is q to the power of k. So it's almost q to the power of k. The reason is that q to the power of k is obtained if we can draw the same set again and again. Usually the number of points that we measure upon, or the number of minimal sets is large, and so we don't really, the difference is not big. So we will ignore this issue. Okay, so the chance of drawing k inliers is q to the k. Okay, so that means that the chance of failing in one round is 1 minus p, which is 1 minus q to the k. Okay. So the chance of failing in n rounds, in all n rounds, will be 1 minus p, or 1 minus q to the k, to the power of n. Okay, so n drawings, right? And the chance of succeeding at least one is 1 minus that. Okay, and that we want to be at least as large as p. Okay, and so this means that let's take the log of 1 minus p should be larger than n times log of 1 minus q to the k. Okay, and from this we know, we get that n, the number of iterations that we need to take, should be larger than log of 1 minus p over log of 1 minus q to the k. And now 1 over log 1 minus q to the k is approximately 1 over q to the k. So this is what we get. Okay. So let's see if we, if q is, sorry, if k is small, then this is, yeah, sorry. So q, remember, is a probability, so it's a number between 0 and 1. And this means that q to the k, 1 over q to the k, is growing fast if k is large, right? So think of it, if q is, I don't know, half, right? Then this 1 over q to the k is 2 to the k. Okay, so for example, if we compare the situation where we want to solve for essential matrices, and there are two possibilities. One is using 5 points, the 5-point algorithm, which we will talk about later in this in the next hour. Okay, and if q is 1/2, that would give us 32. If we use the 8-point algorithm, so a linear, simpler algorithm, this will be 2 to the 8, which is 256, right? The difference can be very big if Q is very small. So if you take, if Q is 0.1, so the number of inliers is only 10%, so 90% outliers, right? Then you get 10 to the 5 times versus 10 to the 8. The difference can be very, very big.
Okay. I think something is bothering me because the log of y minus p is a negative number. Something is, I think, right?
Yeah, I'll check.
Up to.
But it's supposed to be a constant, so I'll check that.
Okay, because you get a negative number on the right-hand side.
It's something about the approximation that is not like before the approximation, it's a negative number divided by a negative number. So
Right.
Right.
Something
So
about,
it should be. So
it's
it should
minus
be
1 over Q to the K.
Yeah. Good point, Heli. Yes. Yeah. Okay. So the sign should be corrected.
yeah.
Otherwise it's okay. All right. Let's take a 10-minute break. Let's say 8 minutes, just so that it will be 10:10 and meet 10. Okay. Okay. Shall we continue? All right. So I fixed a few typos here. Anyway, the conclusions are did not change. So n should be larger than something of the order of 1 over q to the k. And as I said, this implies that in complicated problems, we really want to get a model that requires a minimal number of points. And that's particularly the case with the essential matrix, where we can solve either with 5 pairs of points, or with 8 pairs of points. And so if you use Ransack in MATLAB or in other packages, they will usually use the 5-point algorithm. Okay, we will get back to this, but just that you see what is the difference. Okay. So to solve for essential matrix, so just to remind you first, essential matrix satisfies a bilinear equation, right? Where given correspondences xi and xi bar, so xi and xi bar are points in 2 images, okay? The essential matrix should be gives you this equation, right? So we have an equation for every pair of points, okay? And the equation is linear in E and homogeneous, okay? And if we just use this equation, then there are 8 degrees of freedom. It's a 3 by 3 matrix, and it's homogeneous equation, so you need 8 linear equations to solve for E. However, if you want to do this with 5 points, you can look at constraints over E. The issue is that these constraints are not so simple. One is that the determinant of E is 0, okay, which is a polynomial equation. And the second one is that the 2 singular values of E, so there are 3 singular values. One is 0, the other two must be equal. Okay. This is less obvious, but also this equation can be expressed as a polynomial equation or set of equations. And so overall, we want to solve a polynomial system of equations. And that seems complicated, and it is not simple at all. But there are some ways to solve polynomial systems of equations, and that is going to be the subject of this class. We're going to go through an example, learn one algorithm. There are other algorithms also. It's not the only algorithm, but the main objective is that you get a sense of how complicated it is and how to approach such a problem. Okay, so let's take a simple example. Simple because we can solve it quite easily. Okay, here we have two quadratic equations. Okay, x squared minus y minus 3 equals 0, xy minus x equals 0. And we want to solve them. But we want to develop a general way of solution. Now, I said that this is a simple problem. It's simple because you can notice immediately that the second equation, you can write it as x times y minus 1. And that implies that either x equals 0 or y equals 1. Okay. And if you plug in the second equation, x equals 0, then you get that y is equal to 3. If you plug in y equals 1, then you have a quadratic equation, x squared equals 4. And so y is either 2 or minus 2. And we got 3 solutions in this case. In general,
X is
from
0, y is minus 3, no?
Say it again, sorry?
If x is 0, y isn't minus 3?
No. No. Minus 3, right? Minus 3. Okay. We'll see what happened next. Okay. It should be minus 3. So either there is I was supposed to write plus y there, or we'll see what happens. Anyway, let's ignore this issue, and what we want is to build or to show you how we can solve such a system of equation, and we would want to see that we get the same solution back, whether it's plus or minus 3. Okay. Okay, so how do we proceed? So given a polynomial, we can write it as an inner product between a vector of coefficient and a vector of monomials. Okay, that's clear, right? A, B, C, D in this case is the vector of coefficients. 1, x, xy, y squared is the vector of monomials. And now the vector of monomial is a vector function, right? Given x and y, I get a different vector, okay? So in this case, you see that a solution or a root of this polynomial will be a situation where the monomial is orthogonal to the coefficient. That's, of course, simple, okay? We call mxy a monomial basis. Even though it's a vector, we call it a basis because we can plug in different x and y here, okay? So mxy is a monomial basis. Okay, what we are going to do is to form what we call an action matrix. So the idea is the following. We apply some action on the polynomial, okay? We denote the operator tx. It's an example of an action. The action is multiply the polynomial by x, Okay, this will produce a new polynomial of higher order, of course, right? So, for example, if my polynomial was linear, okay, so the degree is 1, the monomials in the polynomial are 1, x, and y, okay? I apply the operator tx, I multiply by x. Now my monomial is, the new monomials will be x, x squared, and xy, right? I simply multiply them by x. Okay. So the next step is to say the following. I'm given pxy, it was degree 1. I multiply it by x, I get a polynomial of degree 2. Okay. But I want to only consider polynomials which are roots for this polynomial system that we started with. Okay, x squared minus y minus 3 equals 0, and xy minus x equals 0. Okay, these two polynomials. Okay, so I want my monomials, or I want this only to consider monomials in this polynomial system. Okay, so given that, that means that we can now plug in or replace x squared and xy by some things from this equation. So x is good. We are not going to make any substitution here, but x squared we can substitute with y plus 3. Okay, and xy we can substitute with x. Okay, clearly, if we did this substitution, we are still we only apply identities from the polynomial system we want to solve, and so we don't spoil, we don't change in bad way our polynomial. Okay, and what did we do here really? We took monomials, so we had a first degree polynomial. We multiplied by x, we got a second degree polynomial. And using these substitutions, we get back to a first degree polynomial. Okay, so now we can look at the mapping from a first degree polynomial back to a first degree polynomial, given this operator t of x, tx. Okay. Okay, so we started with a first degree polynomial. The coefficients, let's call them AP, BP, and CP. Okay, we multiply by x, we apply the operator tx, and we got a new polynomial qxy. Okay, we did the substitution, and following the substitution, q is also a first degree polynomial. Let's see how. Okay, so we took p, which is AP, BP, CP, like written here. We multiply by x, so now AP multiply x, BP multiply x squared, CP multiply xy. We assume that xy is a root of the polynomial system, which is written here. And so we replaced x squared with y plus p, xy with x. Okay. And now we take this is the first order polynomial, so we rearrange the polynomial. We get 3 times BP plus AP plus CP times x plus BP times y. Okay, I simply rearranged the terms. Okay, and we call these AQ plus BQX plus CQY Okay, so it's a first order polynomial. Okay. And now we want to write this transformation in a matrix form. Okay. And this is how it looks like. Okay, so just look back. Okay. Q is such that AQ is 3 BP, BQ is AP plus CP, CQ is BP. Okay. Sorry. Okay. So we will just write AP, BP, CP here. And you see that the first term is 3 times BP. Okay. AP plus CP. So we get 1, 1 here. And BP. So we get 1 in the middle. Okay. So it's a little bit abstract, so it's a little bit difficult to understand, but what we did here. So feel free to ask questions. Okay, so overall, the mapping Tx in our polynomial system is captured by this matrix. Okay, we call the matrix action matrix. Okay, and look again, this action matrix Mx, which correspond to the operator Tx, takes Cp, the coefficients of the polynomial P, first order polynomial P, and convert them to coefficients for polynomial Q, which happens to be also first order. Okay. Next, we're going to sort of summarize what we've done here and see what happens. Okay. So the polynomial P is Cp times M. Okay. We took the polynomial P, which is Cp times M. M is the monomial basis. Okay. And multiplied it by X. Right. That gave us the polynomial Q. The polynomial Q, on the other hand, is written by Cq times M. Okay. It's also first order. And okay. But CQ we could write as the action matrix MX times CP, right? That's what we wrote in the previous slide. Okay. And now we just open the transpose, we get CP transpose, MX transpose times M. Okay. Now, this holds for any polynomial of degree 1, which means that it does not depend on CP. Okay, so look what we have here. We have XCPM and equals to CP capital M times M. Okay, and we're saying this equation does not depend on the actual value of CP. It was true for any first order polynomial, any selection of coefficients. So we can write this, we can omit CP and write that X times M equals MX times M. Okay. To remind you, M of xy is the monomial basis, in this case 1, x, and y. Okay. This means that the monomial basis should be an eigenvector of M, and X should be the eigenvalue. Okay. So let's see what happens. the eigenvalues of this matrix, so remember the matrix was, this is M, so I can just take the eigenvalues and eigenvector, and let's see what happens. The eigenvalues are -2, 0, and 2, which are exactly the x values of the root. Okay, if you remember, so these were the roots. You're right, it's -3. So sorry for the mistake there. Will be corrected. Okay, so the x values you can see are 0, 2, and -2, and those come out as the eigenvalue in this case. Okay, and the eigenvectors look a bit weird, but really remember that the monomial basis was supposed to be 1, x, and y, right? So we need to scale the eigenvector such that the first coordinate is 1. Once we do that, we get, you see here, 1 xy. So 2, 1 is one root, -2, 1 is the second root, and 0, -3 is the third root. Okay, and that's a solution to the problem. Okay, so let me summarize the steps, the algorithm. Okay, so
Can
first,
you previous slide again? This one, yes.
Yes. What's the question?
I didn't understand what you did there.
Okay, I took the matrix MX, okay, which was this matrix, this one, okay, 0, 3, 0, etc. And because of this equation, I simply found the eigenvectors and eigenvalues. Okay, the eigenvectors will give you the vector of monomial basis, and the eigenvalue should be x. You see that? Okay. So the eigenvalues of that matrix turned out to be -2, 0, and 2. And that correspond to the values of the roots, 0, 2, -2. The x value of the roots. Okay. The eigenvectors, these columns are the eigenvalue, the eigenvectors. Eigenvectors, when you compute them, have norm 1. But the monomial basis should be an eigenvector, but it's really scaled because in the monomial basis, we have 1, x, and y. So the first coordinate should be 1. So we just take each column here and scale it such that the first component will be 1. Okay, so see here, you get something, a different number and the same number. We scale it, we get 1, 2, 1. 1 - 2, 1 should be. 1, 2, 1 correspond to this eigenvector.
Again, why is the first element need to be 1?
Because the monomial basis, because these should give you the monomial basis, and the
Okay.
monomial basis was 1, okay?
Yes.
Okay. 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 So, and the xy are the roots. So we got 2, 1, -2, 1, and 0, -3. Okay. So to summarize the algorithm, given a polynomial system, first we select a monomial basis. What is the monomial basis that we select? It depends on the order of the polynomials in the system, right? So here we used, we had second degree polynomials, and we used monomials only of first degree somehow, okay? Then we apply a mapping to the monomial basis. The mapping that we applied was multiply by x, but you could multiply by y, and you can do, you can multiply by any monomial essentially, okay? Next, we reduce the result so until the resulting expressions consist of monomials from the same basis. So we took monomials for first order, we multiplied them by x, we got a second order, and then we reduced these second order monomials by plugging in expressions from the polynomial we want to solve, the polynomials we want to find the roots for, okay? To reduce it to, again, to first order. That gives us, so the transformation that we obtain is captured by the action matrix. Okay, so we build the action matrix. Okay, we compute the eigenvalues and eigenvectors of the action matrix, and we obtain from them the solution to the polynomial system. Okay, the solutions are in the eigenvectors, and partly they exist also in the eigenvalues. Okay? Questions? Okay. There are some advantages and disadvantages to this procedure. Okay? Any root is an eigenvector of the action matrix, but there could be eigenvectors that are not roots. So we need to check which ones are roots and which ones are not. It's a disadvantage, not a very big disadvantage, but sometimes these matrices could be very big, so it could be a significant disadvantage. Okay. Also, if the eigenvalues happen to be the same, they are multiplicities, and in this case, it may be difficult to extract the roots. Okay, so if, for example, in this case, all the eigenvalues were different. But if, for example, we had 2 and 2, both eigenvalues were 2. So, for example, if we use the action of multiplying by y, you see that there are 2 roots with 1, y equal 1. In this case, the eigenvalue would be, when it's 1, the multiplicity is 2. Now, remember that when the multiplicity is 2, the eigenvector can be any linear combination of 2 vectors, right? So, and not necessarily the 2 vectors that we obtain contain the roots. Maybe their linear combinations contain the roots. And then we don't get an explicit solution for the roots. And that can be a problem. So multiplicities make it difficult to extract the roots. Okay. On the positive side, as I showed now, you can use any action operator. Okay, so you can multiply by any polynomial and produce an action matrix. So if one action matrix give you is not simple to handle, you can try another one. Okay. Questions before we move to the next topic? Okay, so the last topic that I want to tell you is how we solve with this action matrix how we create the 5-point algorithm, how we solve for an essential matrix given only 5 pairs of points. You can imagine that it's not simple. So try to understand. Again, we're giving you just the flavor of how to do that. Okay, so let's remind ourselves. Given 5 pairs of points, each of them is a point in a plane, or really in the projective plane, so homogeneous coordinates, right? We want to solve these equations, so this epipolar line equations with the essential matrix as the unknowns, okay? And we have also the constraint that the determinant of E is 0, and that the 2 singular values, 2 non-zero singular values are equal. Okay. Now, the last equation on the singular values, we want to we can make it look more like a polynomial system. Essentially, we replace it with this constraint. The constraint is 2E E transpose E minus the trace of E transpose times E equals 0. Now, this looks quite complicated. How do we get from this to this one? And moreover, this is a scalar constraint, and this is a matrix constraint. So in fact, there are 9 equations in this constraint. Okay, but let's see that how we can obtain this. Okay, so the essential matrix, we can apply to it singular value decomposition, right? And it will be U times a diagonal matrix times V transpose. The diagonal will contain 2 non-zero numbers and 0 here, okay? And we want these 2 numbers to be equal, okay? Okay. So, so let's take this equation and see that it actually enforces that the 2 singular values are equal, okay? So if you apply singular value decomposition to each E in this equation, okay, you notice that E times E transpose, you get V transpose times V, which is identity, okay? And E transpose E, you get U transpose times U, which is identity. And so overall, you get 2 times U times the diagonal cube times V transpose. Okay, is this clear? The trace is simply the sum of the singular value square. Again, E transpose the V transpose V is identity. So you get that the trace is the sum of the square of the singular values times E. So you get U times, so you get just the singular value decomposition of E here. Okay. Now, U and V can be eliminated here. And the equations you get, essentially you get 2 equations. The third one here is 0. So the equations on the diagonal, you can see them here. These are cubic equations, which can be simplified here. So you get sigma 1 times sigma 2 square minus sigma 1 square equals 0. And sigma 2 times this difference equals 0. And these imply that sigma is either 0, that's the third one anyway, or sigma 2 equals sigma 1. Okay, potentially also sigma 2 equals minus sigma 1 is a solution here, but we know that the singular values are always positive, so, so we can exclude that solution. Okay, so this complicated equation actually captures the constraint that we want. Okay. Next. So again, we want to just remind ourselves. Now we want to solve, we have this equation, the essential matrix equation, the determinant, and instead of the equation on the singular values, we have this equation, or these 9 equations. Okay. So let's first treat this equation. Okay, this is a homogeneous equation that is linear in E. Okay, we have 5 such equations, and E has 9 components. Okay, so we can represent the null space of this equation by, it's a 4-dimensional space, right? So the null space of this equation is 4-dimensional. And we can take a basis for this 4-dimensional space. So this will be called, we will call E1, E2, E3, and E4. these are known matrices. Given these equation system, we know them. This is the basis for the null space. So our solution E must be a linear combination of these four matrices. A1, alpha 1, alpha 2, alpha 3, alpha 4, multiplied by E1 plus E2, etc. Okay? So the solution lies in the null space, and it's a combination of four different essential matrices.
Onan, why do we have four terms again?
Okay, E has 9 components, and we have 5 equations. So the null space is of dimension 4. So we need 4. So usually what's confusing here is that it's written as a matrix. Think of it as a vector now. Vectorize E, think of it as a column vector, okay? And these products of x hat and x bar and x as the rows, okay? So you have 5 vector equations on the unknown E, okay, which has 9 components. So it's in R9, okay, 5 constraints, which means that the null space of the matrix that is composed of the known things x bar and x has a null space of size 9, of size 4, 9 minus 5, okay? And so the 4 vectors that span the null space, now rearrange them as matrices. These are E1, E2, and E3, and E4. Okay, and a combination of these 4 vectors will be our sought solution. So now the unknowns are simply alpha 1, alpha 2, alpha 3, and alpha 4. Okay, and E1, E2, E3, E4 are the basis vectors which we know, basis matrices. Okay, now because this spans the null space, because these are homogeneous, I can scale E. I can scale the solution, okay? And so what I will do is choose alpha 1 to be 1. This will be only problematic if alpha 1 should be 0. But in general, this is not problematic. So I'm going to scale alpha 1 to be 1, and I'm left with 3 unknown, alpha 2, alpha 3, and alpha 4. Okay? Good. So I know that the form of the solution should be E1 plus alpha 2 E2 plus alpha 3 E3 plus alpha 4 E4. Okay. And now I want to plug this form of the solution into the other equations. Okay. So we have two types of equation. We have many equations, or 9 equations of this form, okay? So we plug, for every E, we plug in alpha I, alpha J, alpha K, which are 2, 3, and 4, okay, times, okay, so what did I do here? I replace E by 1 plus alpha 2, let's call it, by alpha 1, which is 1, E1 plus alpha 2, E2, plus alpha 3, E3, plus alpha 4, E4. When I do that, I get products of E1 and E2 and E3 and E2, E3, E4, E1, E3, E4, etc. Right? I write these products, so I get sum. I goes from 1 to 4, J from 1 to 4, K from 1 to 4 of these kinds of products. Alpha I, alpha J, alpha K, EI, EJ, EK, EI, EJ, EK. Okay. So this is the first thing I do here. I do the same thing with the determinant. Okay, so I want to write that the determinant of E equals 0. Again, instead of E, I put alpha 1, E1 plus alpha 2, E2, etc. Okay. Now remember that the determinant of a 3 by 3 matrix is simply product of 3 entries sums of products of triplets of entries. And so again, I get a form like this, where ELMI is the LMth entry of EI. Okay, so this looks complicated, but it's but overall this is not too complicated. It's the principle is simple. Okay, overall we have 10 constraints, right? There are 9 equations here and 1 equation for the determinant. Okay, and the number of unknowns are 3, right? Alpha 2, alpha 3, and alpha 4. Okay, and you see that these equations are cubic in the alphas. Okay, we have products of triplets of alphas. Okay, you can remember that alpha 1 is 1, so you get triplets, you get pairs, you get, okay, because sometimes these alphas are 1. Okay, overall we have 10 equations of cubic polynomials. Okay. So what we are going to do is build a monomial vector. Okay. The monomial vector will contain our unknowns, the alpha 2, alpha 3, and alpha 4. Okay, up to cubic order. Okay, there are 20 entries for this monomial vector. Okay, and the coefficients will be 10 by 20 matrix. Okay, 10 because we have 10 polynomial equations, and 20 monomials. Okay, so Cm equals 0 gives you all the polynomials in the equation. Okay, what we do next is we take this 10 by 20 equation and perform Gaussian elimination. Okay, that would make, this will give us a diagonal matrix in the first 10 entries and some coefficients in the second part of the matrix. Okay. Now, the way we order the monomials is that the cubic monomials appear first, and there are 10 of them. This means that every cubic monomial can be replaced by a quadratic polynomial. Okay? So if you remember in the example that what we did was to say that every quadratic monomial, we replaced it by a linear polynomial, right? Remember, like x squared, we replaced by some y minus 3 or something like this. So this elimination allows us to do the same thing with the cubic monomials. Okay, so cubic monomials, if they are roots, they are equal to some quadratic polynomials. And next, we form an action matrix. Okay, we take a quadratic polynomial, second order. Okay, we multiply them by one of the alphas. So let's say alpha 2. Okay, we can choose any of them. Okay, we get a cubic polynomial. We use this matrix to replace the cubic term with quadratic polynomials, and that gives us the action matrix. Okay, and next we simply find the eigenvectors and eigenvalues of this action matrix, and that gives us the solutions to the polynomial set. Okay. So of course, this is too complicated to show with an example, but I think you should have the idea of how to solve this. I think you can even solve it with this information. Okay. So once we solved, we did the eigen decomposition, the eigenvectors give us the values of alpha 2, alpha 3, and alpha 4. And that immediately implies E, because we simply say E is 1 plus 1 times E1 plus E2, alpha 2 times E2 plus alpha 3 times E3 plus alpha 4 E4. And E2, E3, E1, E2, E3, E4 are simply the basis of the null space of the original 5 equations on E. Is it clear?
Why do we do Gaussian elimination?
Okay, so let me go back to the simple example, and then I think it should be clear. Okay, critical step in producing the action matrix was, where is it? Here. Was to take a first order equation, polynomials, a general unknown first order polynomial, apply the operator tx, which is multiplied by x, to obtain a second order polynomial, and then use the polynomial system to go back to a first order polynomial. Okay. How were we able to do that? Okay. The reason we were able to go back to the first order polynomial was that we had x squared here, which happens to be equal to y plus 3, okay, from this polynomial system, and xy, which happens to be x, okay? If we had y squared here, we were unable to go back. So the polynomial system here doesn't tell us how to go back to a first order, okay? Sorry. Okay. So this was in a sense luck, right? The luck was that x squared was, if we had x squared plus y squared, for example, here, again, we were unable to go back to a first order polynomial. How can we go back in this case to a first order polynomial? We have to sort of rearrange our polynomials such that we will have only one second order monomial in every polynomial, and all the rest will be first order polynomials. And that we can do with the Gaussian elimination. Okay, so the elimination was meant to take all these 10 equations that we had in this case. Okay, so we had the 10 constraints here, and rearrange them such that cubic monomials plus quadratic polynomials will be equal 0. Okay, and this is a manipulation that, if you think about, you will see that you can do that, because polynomials are linear in the coefficients. Okay, so it's really a linear system over the coefficients, and you can rearrange this system, okay, by multiplying it by scales, by subtracting polynomials, in order to do this Gaussian elimination. Okay. Once you have this equation instead of this one, you have, for example, x cubed plus a second order polynomial equals 0. So if your action gives you x cubed, you can replace it by the second order polynomial. Is it clear? That
Yes.
allows you to build the action matrix.
Can you also explain how did you build the alpha? How did you said you plug the sum to three sums of 1 to alpha ijk, yes. How did you go to this?
Okay, you simply plug in this. This is E, right?
Yes.
Okay. You take this and plug it here. Okay. So every E here you replace by alpha 1, E1 plus alpha 2, E2 plus alpha 3, 3 plus alpha 4, E4. Okay. Now you have three terms like this and you multiply them. Okay. So you get alpha 1 E1 times alpha 1 E1 times alpha 1 E1. Alpha 1 E1 times alpha 2 E2 plus times alpha 1 E1, etc. Okay, you simply open these summations, these products, and you get sums, long sums of triplets of like this. Okay, all combinations of E1, E2, E3, where the indexes are between 1 and 4. Okay, so it's very simple.
But we don't have 4 coefficients. Why we have only 3 alpha 1?
Oh, because we have we have 4 coefficients. This is why it goes up to 4 here. But we have only 3 terms, right? In every product.
Okay.
Okay. Okay, so you have 3 terms with I, j, and k between 1 and 4. Okay. So it's, the principles are simple. It's just long. That's all. Okay. More questions? Okay.
How did you get E1, E2, and up to
Okay,
E4
good.
again?
That was the other critical step. So there are 3 critical steps here, right? So again, let's look at the 5 equations of epipolar equations. Okay. These 5 equations are 5 linear homogeneous equation in E, where E has 9 components. It's a vector in R9 or a 3x3 matrix. Okay. This means that the solution must lie in the null space of these 5 equations. So it's in a 4-dimensional space. Now I want to produce a basis to this space. Okay. And the basis to this space is given by E1, E2, E3, E4. Now, if I wrote this as a vector equation, it would be very simple to you to understand, I think. It's just a little bit.
What I don't get here is that E is unknown. So how can you?
Right. E is unknown, but the space is known from X1. Okay, let's give an example. Suppose you have, let's think of a 3-dimensional space and you have one equation. Okay, so you have, let's say, 1, 1, 1, 1 is the coefficient times XYZ equals 0. Okay. I claim, and I think it's you should agree, I think, that XYZ must be a combination of 2 vectors that I can write explicitly. I don't know what combination. I don't know the coefficients of this combination. Okay, but okay, so X plus Y plus Z equals 0. This is the equation. Okay, and I say, well, given X, I know that Y plus Z should be minus X. So I can't do it offhand without writing. But you can find two vectors that such that alpha of the first vector plus beta, the second vector, will be your solution. So you simply find a basis to the null space. Okay, so one possibility is to simply take any vector that is orthogonal to, okay, so let's take again this example, x plus y plus z equals 0. Okay, so I take 1, 1, 1, 1, 1, and find two vectors that are orthogonal to 1, 1, 1. Okay, one of them is -1, 1, 0, right? The second one is -1, 0, 1, right? You agree that those two vectors are orthogonal? Okay, now I claim that x, y, z must be a combination of these two vectors. So it will be alpha 1 times 1 minus 1, 0, plus alpha 2 minus 1, 0, 1. Okay?
Mm-hmm.
So these two vectors that I now gave you are the E1, E2, E3, E4. Okay? This is the basis.
Okay.
Okay? Okay, I hope all the steps are clear. I think it's good to go through this again, listen to the recording, maybe play with a small example. Okay, to summarize, finding optimal model given measurements, that was really the subject of this class. It depends on the noise model. So we showed what we do with Gaussian noise, which yields either linear least squares or total linear least squares for linear problems. Okay. We talked about outliers and how you can use ransack to remove outliers. Okay. And then we said that for ransack, we need minimal solvers. We need to solve with minimal number of equations. Okay, and we talked about one method from algebraic geometry, how to solve polynomial systems of equations, and how to do this for the 5-point solver. Okay, by applying eigendecomposition to an action matrix. So this is all. If there are more questions, I'm happy to answer. And if not, next week. Who's teaching next week? Not sure.
Ani.
Okay, Merav is teaching. So thanks.